Sorry, keep you waiting for me to fix the pen device. This one is not working. Could you see the screen? The Word file chapter 10. Can you see the screen? The Word file? Okay, good. Now let's continue lecture on the pile construction. Okay. Now I think we have talked about what's template casing, right? Template casing. You know, the steel pipe, right, driven into the ground, and then use the grabber, right, to excavate the soil inside that template casing, the steel pipe, right? And then after the excavation, we will put up the steel bar, right, the reinforcement bar, and lower it, what we call the steel cage, right, this steel cage down into the hole, and then we trim it pipe to place the concrete into the, into the hole, right, with board, and then we will, after the concrete placement, during the concrete placement, the steel pipe or the template casing will be extracted, right, slowly, right, until, right, the whole steel casing was removed, and then the hole, right, will be completely filled with the concrete, right, with the reinforced concrete. So that is the ball pile construction, right, using the template casing. But what about the other technique? The slurry trench method, right? The slurry support method. Well, in the slurry trench, we will use the grabber of the clamshell. Okay. We have this. There should be a. This, you can use this method, right? The clamshell. Sorry. Okay, the clam shell, which is in fact, a very heavy machine, like the crab, right? The seafood, like the crab, and then this clamshell will, right, open the door, right, and then grab the soil, right, and then by raising the clamshell, you have the soil, okay, excavated from the bottom of the hole. Now, in the meantime, during the excavation, you have to use the drilling mud, sometimes called the bentonite, right? Bentonite. Now, the bentonite will be slurry, right? A specific, soil material, which will give you what we call the amphisotropic, right, properties. In other words, if the fluid is allowed to stay a while, there will be a setting of this fluid, becoming a solid, right? And when being agitated, it behaves like a liquid. So that will give you a very good support, right? Support to the trench during excavation, support to the wall, right? So the wall will become standing stable, And the bentonite will use the fluid pressure to support the penetration of groundwater, right? Because there will be a layer, what we call the gel structure, right? The gel here. The gel structure will become a filter cake, right? A filter cake. This filter cake, which acts as a impervious layer, right? To stop the water, the groundwater seeping right into the trench. Now this will make the the trench very stable, right? Even though there's a high groundwater table, right? The groundwater table will be supported against from being going into the trench by means of this bentonite slurry. Right? So it's important to maintain the bentonite properties so that it has this sort of ability, right? So in other words, we have to conduct various tests, including the viscosity, density, and fluid loss, and also the cake thickness, right? Now, all this means that we are monitoring the quality of the bentonite to see whether it's good enough to support the trench, right, from being collapsed. And if we find that there are too much slurry loss, then you have to, replenish it, right? You have to add new slurry material, right, to maintain the solution. That solution is called the suspension, right? The suspension of the liquid. Okay. Now, at the base of the bore pile, sometimes we want to an enlargement. What's an enlargement? The bailout, right? The bailout, sometimes called bailout, right? Just like a bell, right? Sitting on the on the table, there's a bailout structure. Now, the increased base area will give you the higher bearing capacity, right? Because you have the larger area, base area, rather than the diameter of the bore pile. So you have to make the enlarged base, right? So that you have larger base area to reduce the bearing pressure on the rocks, right? That's the bearing pressure, right? So that you have a higher rock bearing capacity, right? Because of this increased or enlarged base area. Now, sometimes it's called the underrimming, right? Underrimming. So you can see it here. You can see the teeth here, right? The teeth. Now, when the hole is rich down there, right? Okay, then this will be extended out. This teeth, right? This length of teeth will be right. Will be extended out, right? Extended out, and you have the teeth, and after you rotating it, so this rotating part will be further extended, right, to give you a larger, the enlarged base area, right, after the excavation. Now, of course, when you are doing that sort of what we call the underrimming, right, or enlargement, right, enlargement of base. Now you have so many, the rock fragments, right? You have lots of rock fragments. Because of this enlargement, you have rotating, right, your device against the rock, the hard rock, so that it will be broken into smaller pieces, the fragments. After you have, you have come up with this shape. Now, before the concreting, or lowering of your reinforcement cage, you have made it, the base here, right, must be very clean, right, clean and clear from any debris. There should be no black debris, right? No smaller parts or the fragments there. So you have to clean by what? LCD, right? Reverse circulation drill plus what? Airlifting. You know, when there is the the LCD device installed, right? There will be a pipe, and the compressor will be released at the base of that pipe, so that the compressor air bubbles will go up, right, to the surface. All this bubble, right, air bubble will rise up together with the debris, right, so that it's pumped out, right, and you got a sedimentation tank where all these rock fragments, right, will be settled down there. So when you continue the airlifting until the surface, right, give you a very clean surface there. Now, by inspecting the quality of the water sample extracted here, the first sample will give you a lot of fragments. Now, after several hours of airlifting, then you should come to see there is now clear water, free from any debris. That means the whole base has been cleaned, right, with this airlifting operation. And by checking or monitoring the the cleanliness of this base area, then you can proceed with the the lowering of the reinforcement cage and the subsequent concrete placement. So that is the the typical process of how bore pile and its enlarged base area could be formed into this shape, right, by by these underrimming machines and subsequent airlifting. Right? And the concrete placement will be carried out by the trimming method, right? And you know what's trimming, right? You use a down pipe, you place the concrete into it until there's the concrete, the concrete here, the concrete is going down, right? And then it come out from the bottom of the trimming pipe, so that you have to maintain a minimum of embankment. Embankment, right? In other words, you have to make sure the concrete outside the trimming pipe will have a certain depth of penetration. So the concrete here, right? The concrete will flow out from the bottom of the trimming pipe, and you have maintained this minimum depth of embankment. Now, this will give you the concrete, right? Newly placed the concrete to push the previous pour, right, up to here, right, upwards, so that when you continue the concreting, so the concrete surface level will rise up until it totally displays all the bentonite from the hole, right? It displays all the bentonite from the hole, and now we place with the very wet concrete mix. Now, in the trimming concreting method, don't need any vibration, compaction, right? You don't need compaction of concrete, because the concrete will have a very good flowing properties. This kind of concrete is sometimes called self-compacting concrete. In other words, by its own weight, the concrete could be compacted very well, right, with its own weight. You don't need and you don't need any external vibration. You don't need the vibrator. Okay, so the allowing the frame of the concrete is already good enough to compact the concrete, right, by its own weight. Okay, that is the trimming method. Now, of course, when this trimming pipe and that is the concrete going up. Now, often you have this is the cut-off level. Now you allow an additional 750 millimeters, right, concrete, right, coming up to this level, and then you remove that part, right, because these concrete are usually contaminated, right, with bentonite, right, by bentonite. So that's why we have to remove, right, this additional 750 millimeter concrete, right. So remember that you should go your concrete, right, from concrete level further 750 millimeter, right, and this poor quality concrete has to be removed, should be hacked off, right, to be removed away. So until you come to this cut-off level, that should be giving you a very good quality concrete, but not for this 750, right? So any question about the the slurry supported pole pile construction? I think you have come across those knowledge, right, in your construction technology or material course, right, some sort like that. Is it true? You have learned about it before, right? Now, pile loading test. Now, for any pile installed in a construction site or in a foundation contract, now we need to carry out the pile loading test to make sure the pile installed should have the desired capacity, right? Because all these pile foundation will finally will be supporting the superstructure, right, above the ground level. So we have to carry out that sort of loading test to make sure every pile should be good enough. Now, how can we carry this pile loading test? Right. Now, here for the cast in place concrete, the pile should be, the testing of the pile should be carried out when the concrete is at least, right, 7 days and has the strength at least twice of the maximum applied stress. In other words, if the concrete is too young and you apply the loading test, now that will cause the concrete damage, right? You don't want that, right? So you have to make sure, the strength of your concrete, right, after placement should have adequate strength to support our loading test. Right? Now, at least you have a factor of safety of 2, right? Twice the maximum applied stress. In other words, if you are going to support 1,000 tons, say 1,000 tons, make sure the concrete strength should have 2,000 tons, right? Because the load is 1,000 tons, but our strength of the capacity of the concrete should be able to be loaded, right? 2 times of our loading, right? 1,000 tons, 2. So we have a factor safety 2, right? Now for clayey soil, right, say for the friction pile, then you have to make sure when the pile has been driven, you have to wait for at least 3 days so that the settlement of the driven pile should become stable, right? because if the pile is still moving, then you should not apply the loading test. Now this is particularly important for the clay soil, right? The clayey soil, because this clay soil the settlement takes time, right? You have to allow the time, at least 3 days, right? So that the settlement is becoming finalized. Now, usually we will do what we call the canage. Okay, means what? Heavy weight, right? That's called canage. So you are piling up things, right? Concrete blocks, so that it becomes a huge load, right? Sitting on the top of a pile. So it's a static test, right? A static load test, right? A dead load test. As you can see from this photo, you can see what you can imagine, right? That's a canage. A pile, right? A stocking of things, right? Of concrete blocks. Now you can see the arrangement here, right? Now here is the canage blocks, right? So that is the heavy weight, and then you have the steel I-beam, right? The I-beam, right? I-beam edge. So you have, right, the steel piles, right, perpendicular to this, to this page, and in the 90-degree direction, you have this horizontal layer. So you got, here, right, and then you have a grillage of the I-beam. So that's I-beam here, right, and here is the horizontal one. Both are horizontal, but in orthogonal direction. They are perpendicular to each other. Now the horizontal one, right, will eventually support, right, the canage load through these, 1, 2, 3, 4, 5, these 5 steel I-beams, and this loading will be carried by these, rows of the, the horizontal beams. Now, and it will be sitting, right? Again, this I, right? That's I. Okay. Now, these 2 I-beam will apply, right, the loading to this pile. Okay. Now we measure the load cell, right? The load cell means what? It's a hydraulic jack, right? When you increase the oil pressure, it will move up, right? Now when you are adding the loading, so if you are increasing loading, right, the oil pressure, the hydraulic oil pressure, so you have a greater vertical load, right? Because it's going to try to, right, move upwards, right? So it will going to support the canage, the upper concrete blocks. Okay. Now, because when it's going up, at the same time, right, by action and reaction, you are adding the loading onto the pile, right? The pile is down below. So in other words, when you are increasing the oil pressure, right, this piece will try to go up. At the same time, it will press, right, the pile underneath into the ground. So that's the pile load. Now, of course, it's very important that suppose you have a, say, 3,000 tons, right? Now, when you add a hydrocarbon, right, and at the same time, you are pressing the pile downwards. Now, make sure, right, that could be 2,000 tons, leaving, some reactions there. Say that is, say 2,500, so that is 250, 250. So it means that the carriage will be at least have 3 supports. Now, do not allow this hydraulic jack to have a jacking force total 3,000 tons. Now that would become, the whole mass of the concrete block unstable. In other words, you always keep, right, there should be some reaction forces there. In other words, if you try to, right, apply a test load of 2,000 or 2,500 tons, so you should add something more, right, at least 3,000, so that there will be some, right, reaction forces on the 2 sides. In other words, the carriage is supported by 3 support rather than by single support. So you understand the purpose why we have these 2 supports, right? Because in any instant you should need 3 supports, right, to support a heavy load, right? 3 support. Of course, there should be a pile, right? This will give you a pile loading test, right, to the pile. So can you imagine and understand what I have explained to you, right? What's the carriage loading test? Yes or no? You understand this carriage flow or pile loading test? Good. Okay. Now, for this arrangement, it's somewhat different. Now, this is not going to using the carriage loading principle. Instead, this is the pile test, right? The pile test arrangement for this pile to be tested. Now, on the 2 sides of the test pile, you have driven 2 anchors, right? 2 anchors. That's the left anchor and the right anchor. Right? Now, when you are jacking, right, at this position, so you are trying to lift, right, this horizontal beam upwards, while at the same time you are adding a loading onto the test pile. Now, under this uplifting force, right, for this, that's the, that's a frame. When there's a force, try to lift this, the frame upwards. At the same time, there will be a anchoring force. So F is equal to reaction 1 plus reaction 2, right? In other words, F is equal to R1 plus R2. Okay. Now that F is again this F. So that is the force applied to the test pile. If you want to have a larger F, here, that means you have a larger R1 and R2. In other words, you should, right? You should drive a long anchor pile on the 2 sides of this test pile. You don't need to put up with any carriage load here, right? You are not doing the, the carriage loading test. Of course, the drawback, right, the disadvantage of this pile loading, what we call the reaction pile. What's the disadvantage? You have to install these 2 piles, right? Okay, this is additional cost. It's just at your own expenses, right? Because they are installed just for the purpose of doing the pile loading test. So that is, it's a wastage of the investment, right, for this pile loading test arrangement. So that's not common, right, in Hong Kong, by doing the anchor pile, right, installed, right, just for the purpose of doing the pile loading test. This guy is very famous. a very famous foundation engineer, right? M.J. Tomlinson, right? M.J. Tomlinson, a very famous guy, right? This guy, right, has written a very famous book to, you know, to discuss how the foundations should be designed, right? Particularly the power foundations. Okay, now the test procedure. Now, for the test procedure, you have to, you know, say for a pile, right, load, say if the design load is, right, 2,000 tons, then often we will test the pile 2 times. In other words, 4,000 tons, right? Whether the pile could be, right, to be tested to receive that double of the design load, right? So 2 times, right, of the what we call the working load or design load. Okay. Now we often apply what we call the ML test, maintain loading test. Say for 4,000 tons, you come up with, say, 3 stages, right, or 4, right? Say 0, and then 1/4 of it, 25%, right, 50%, right, and then say 100%, right? So we increase the load, right? Say from 0 up to what? Right, 1,000 tons, and then we come up 2,000 tons, and then come up with 4,000 tons. Now, from 0, right, to 1,000, you have applied the load, right, 1,000 tons, and then you should allow this 1,000 test load, 1,000 tons of test load to be maintained for a certain time, right? You should not say increase up to 1,000 tons and then, you know, check the power settlement and then follow up with another 1,000. You should not do that in that way, right? You should allow this 1,000 ton, right, to be maintained for a period, right? So you apply the load, right, to be maintained for a specified period, right? Say 24 days or so, right? Or you should check, right? There's an initial, right, in the power settlement at a very fast rate until the settlement rate slows down to a certain degree, right? And then with slowing down of the power settlement, then you can proceed with the second loading stage, right? So it's important, right, to apply the maintain loading test, right? Okay. Until the rate, right, you should maintain the load, right, until rate of movement has reached to acceptable low value. So the settlement has been slowed down, right, before you add the second load increment. So that is called the ML test, maintain loading test, right? You should not add the loading too fast, right? You should allow the time for the power settle to a certain degree, right, until it slows down, right, before you complete the second stage. So that is the principle of the power loading test procedure. You should allow the time for the load, right, to be maintained for a certain period until the settlement of the power has come down. Okay. Now, and of course, you need not only the load cell, right, the load cell to record the loading, right, the power loading of powers. But you also also need to, you know, to maintain, right, and monitor the power settlement. pile settlement. So in other words, the pile load and also how far the pile will go down. Now you can see from the canage, right? The canage loading arrangement. You can see the dial gauge here, right? But this dial gauge measure how far the top of the pile will go down, right? So it's important to monitor, right, the settlement of the pile, right, is being loaded, right? Throughout the whole testing period. You have to make sure have a true record of the the loading and also the corresponding settlement of the piles. Now here are the typical, right, load against settlement curve here. If you increase the loading, right, the loading increase, the settlement becomes more and more, right? Now if the pile is installed, right, in firm or to soft clay, right, or loose sand, then you come up with this, the increase of the loading together with the settlement, right? This behavior, right? Now, here you may imagine that should give you, the failure load, right? The pile load, right? At which we say that the pile will fail, right? Because there was so large the settlement upon the loading. So you have a very, a very typical, right, a clear the failure load of this pile. Now it's a part of the friction pile, but it's stiff clay. You don't have that sort of characteristic or that sort of behavior, but you have this a peak and then past the peak and then will go down. So the loading will be decreased, right, while the settlement continues to increase. Okay. Now you have different sorts of the pile behavior, right, in different various types of soil. Right? Okay. Now it looks very strange, right? You can see there's two steps, right? So once it looks that the pile will fail at this low, but suddenly, right, after a certain settlement, it hard again. So the you need to increase further loading, right? It looks that the soil becomes hardened, right, until you got a second stage of the maximum power loading test. So there's a gap there, right? That gap here. So you thought, right, in the first site, right, you thought that that is the failure load here, right? But if you continue this testing and pass this settlement, the pile will take up the loading, right, a further stronger loading until it failed at a second stage. Okay. Now sometimes the weak concrete will fail first, right, before, right, the true curve. Right? So in other words, the pile may fail because of the concrete, not because of the capacity of soil. Right? So that gives you a wrong picture. You thought that the soil is too weak, but it's due to the weak concrete of your pile shaft. Right? In other words, these piles, right, so despite that is a very good soil here, right? Good soil or good rock, right? But you apply the loading, the concrete is too weak, right? The concrete, right? The concrete pile fail first, right, before the bearing failure of the rock underneath. Now let's talk about the criteria, right? The criteria of POW's test acceptance. Right? How does POW will be accepted after testing? Now, let me tell you about the very famous 90%, right, criteria, right? According to the the civil engine works specification. Now, suppose you got that is the load, and that's the settlement, right? Okay. Now, when you apply the loading, the loading increase onto the POW, then you have a larger POW settlement, right? Very straightforward, right? Now, until then, okay. 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 Now, that's the load. That's the settlement. Okay. The settlement of the POWs. Now, if for a certain loading, say here, right? Imagine, that's the P, right? The P, when you come to 90% of the value of the P, then you mark the settlement, right? 0.9 P, right? So at the 90% of the failure load, and then that is the settlement. Now you double it. So this one, double it. So that is what? 2 delta 0.9 P, right? Now, if the POWs come up with 10, in other words, when you increase 10% more, and then you have got your settlement, right, of equals to 2 times of the settlement at 90% of failure load, then this POW is acceptable. It's okay. What about here? If a POW okay, say here, okay, but you have a larger settlement. So this is greater than 2 times the the settlement at the 90% of failure load. Now this POW cannot be accepted. This POW could not be accepted. Right? Because at 10% more, the POW settles much more than 2 times of the settlement at the 90% of the failure load. Okay, so this one is good, but that one's bad. So this is bad, and here's good. Say, what about for the POW? Say here, right? You got this POW. So when you increase the loading from 0.9 P, right, you have that settlement. It's smaller, right? The settlement at the failure load is smaller than 2 times that, right? Say if that is, say 10 mm, suppose that's 10 mm, and you got only, 70 mm, so good, right? That's okay, good. But what about for this part? Yeah, right. Say 25 or 20 mm. So this cannot be accepted because when you double, right, 10 mm, so it should 20 mm, right? It should be 10 mm, 20. But you got 28. So this part could not be accepted. Now that is what we call the first 90% criteria. Right? So for the loading, right, is increased from 0.9 P to the test load if the deflection go beyond double the deflection at the 90% of the test load, that part could not be accepted. But if the settlement is less than, right, 2 times the 0.9 of the test load, then the power is passed, right, under this loading test. Okay. Now there are other criteria not only for the civil engineering works, but also right, to be required by the BD, right, the BD, and also the housing authority, right, HA, right, the housing authority. Of course, the BD will have control over the private project, right, private building. But for HA, that's the public housing, right? Okay. And the criteria A is for the the infrastructure, right? Infrastructure, right? The civil engineering project. Right? So basically, there are 3 different criteria, right? Adopted by the 3 important sectors of the local construction industry, right? For civil engineering works, for the private building, and also for the public housing. Okay. Can I rotate? How can I rotate? Okay. Now you can see here, 2 times, right? 2 times, right? 2 times the 0.9 of or 90% of the test load. Right? Now for the private development, say for the the buildings department, right? The diffraction or the settlement of the power will be working according to this formula. Okay, the QL, that is the, first of all, that is the elastic part, elastic settlement, and then you come up with the second part. It depends on the diameter of piles, the diameter over 120 and plus 4 millimeters, right? So the diffraction should not be greater than the sum of these three portions, right? Okay. Okay. The housing department adopt similar formula to the BD, right? Okay. Now, of course, we don't want to look into the details of this acceptance criteria. Now, basically, they are the maximum diffraction consists of two parts, right? The first part is the elastic one, right? Remember the Hooke's law, FL over AE, right? That's the elastic part, and then the second part is the something related to the diameter of the piles, right? With a certain percentage, so 1/30 times the diameter of the piles. Okay. Now, I think we'll stop here for our pile foundation. Okay. Okay, MJ Tomlinson, very famous guy. Right. Okay, I have completed the chapter 10. Are there any questions for chapter 10? No question? Now, I just want to remind you, right? You have to hand in the assignment 10, right? By midnight tonight. Okay. And do you have any news about your exam? Date, time, and venue? So you should have got all those data, right? Yes or no? Which date is the examination date for this course? Any idea? So the date of the examination for this course, the time and the venue? No one knows? Tenth of August. Are you kidding? 10th of August. It's a rumor, right? Are you sure? Any other news? Any news other than 10th of August? Come on, you should know the date, the time, and the venue. And you have received an email or some sort of announcement, right? There should be some exam schedule sent to you already, isn't it? No one there to say something about the date. There is an indication to sit on for the on-campus what? Invigilator examination in August 2020. Anyone to know about this date? 25th of May? HHP? No one knows this arrangement? Yes or no? There's a change in the exam schedule, are you sure? I see. So you have two choices. Do you? I see. Okay, so I don't know that. There are two choices. To me, I only receive an email that there should be the, anyway, you should rely on the information, all right, the black and white document, the academic management from me, right? Because I'm a part-time lecturer, so I don't know what sort of the document sent to you. Okay, please be carefully about any documentation regarding the exam schedule for this course. Not from me, right? Because the academic management will have a higher authority than me. Okay. Okay. Any question about the lecture notes, right? Or even the PowerPoints or the assignments? Anyone has received the mark assignment 9 to send to you through the email? Anyone has got my mark assignment 9 through my email? Yes or no? Assignment 9. Mark. Not yet? Okay. I have marked all the assignment already, so I hope I can send you the assignment 9, right, after marking. Okay, any question about the course here? Because we have come to the end of this course. Now I will do the some revision work, right, for the rest of this lecture and tutorial tonight. So are you ready to do the revision? Yes or no? Now I will tell you I have got something from the subject leader of this course. The past exam paper solution. Exam paper. Answers. Well, I got for a few years, right? 18, 19, and then 17, 18 academic years, right? And then, okay. So, Mr. Lam, right? You haven't got the assignment 5 and 9, okay? But I think I have sent all the assignment 5, right? Did you submit the assignment 5 late? Or you submit the assignment 5 in time or late? I don't know, so I can't remember. If you submitted your assignment in time, you should, receive my mark assignment, just like the rest of you, right? In the same batch, right? Okay. Now I will have the numerical answer. I have the numerical answers. Okay. So if you have tried your best, right, to do the past exam papers, okay, I got those numerical answers for you to check, right? But before I give you the numerical answer, you should show me the work you have done, right? Otherwise, I will not give you the numerical answer. So that is the practice right here. So if you want to get this numerical answer, not solution, right? The solution will be highly confidential and restricted, right? So I will not give you the solution, but I can give you the numerical answer, okay, for you to check. Now, before you can get the numerical answer, you have to show me, right? You have done, you have done your work, right, for the past exam paper. Otherwise, I will not give you the numerical answer. Right? That's the weight here. So, is that clear to you? Now, I have some comments on your assignments. I found quite a number of you very, very poor quality in terms of, readability. I believe that some of you have just used your, the mobile phone, right? And then give some shots on your progress, and then send me the PDF. Now, I have found quite a number of you have got your assignment very blurred image. That is no good, right? Very blurred. It's hard to read, right? right? You are studying at the university, right? You should right. You should have your work right completed in quality. Okay. Nowadays, you have so many technology available. So why not? Why don't you good quality work, right, and show to me? So it's a pity, right, and disappointment to me, right? Very poor quality, right, of your not only the printer quality, right? I mean the visual quality. It's too bad, right? So that may affect my marks to be awarded for those assignments. And as a usual practice, I think you should write down your student name, right? Your, the student number, and also the topic of the assignment, and so on. Right? Rather than just leaving me several pages without names, without any identity of you, right? Except the file name. And some students may just send me the file, right? Without the proper file name, right? Without the student identity. So it's difficult for me, right, to trace your test email, your email of the assignment and see who are they, right? Okay, anyway, now I wish to use the PowerPoint, right, to do the exam revision. So are you ready for the revision? Because tonight is our, the last meeting. So I think most of you would like to have doing some revision, right? So that you have better prepare for your examination. Okay. Okay, then I will go for the PowerPoint first. Okay. Okay, could you see the PowerPoint? Okay, good. Okay, stresses and so on. Now, for for the geotechnical world, the engineers stress the importance of doing the lab test, right? The lab test for the shear strength of soil, right? Shear strength of soil. So they have to prepare some soil specimen, whether the soil sample are taken from the site investigation, right? They they take the undisturbed sample from the depth of the depth of the soil or below a certain depth below the ground surface, and then they trim, right, the soil specimen into, right, appropriate sizes and dimension, and then put it under the test, right? In the soil stress or the shear strength testing, we employ what we call the triaxial test. Now, in triaxial test, so there is a span sample, there is a soil sample, right? First of all, you have applied what we call the sigma 3, right? The confining stresses. The confining stresses, sigma. And then, so sigma 3 and so on. And then you apply a principal stress, right? Sigma 1. Sigma 1. Okay? Now, first of all, before we apply here, the sigma 1, before we apply the sigma 1, initially, in free direction, you have the confining test. Confining means the stress all around, right? Whether X, Y, or Z axis. And then this confining stress will be constant, kept constant. Constant. So there will be no further increase of the confining stress. And then we apply an increment, sigma 1 minus sigma 3, so that will give you sigma 1, okay? Sigma 1 minus sigma 3 plus sigma 3. So on top of the confining stress, right, you add this additional stress, that is called the deviator stress. So this is called the deviator, right? Deviator stress. Because it's different, right, from the confining stress. Because in the confining stress, X, Y, and Z, right, are all the same, except for for this vertical stress. You have to deal with, right, from the confining stress by adding an extra stress. So that is the extra stress to the confining stress. So the extra stress plus the confining stress will give you the sigma 1. So that's how the name comes from, right? The deviator stress. Okay, having those concepts, then we come to here. Say you got right deviated stress. Right? Okay. So remember that sigma 1 minus sigma 3 and confining stress here. Right? Say MPa. Okay, so that's sigma 3. Say here you are given that, say that is 200 MPa, and you got 150, right? And then you got 250, right? The confining stress, say, is 200, right? And so on. So when you are going to plot the stress strain graph, so you have to work out what is the sigma 1 first. So what's the sigma 1 MPa? Very easy, right? The deviated stress plus confining stress will give you the sigma 1, right? That's the deviation. So this one, right? Sigma 1 minus sigma 3 plus sigma 3 give you the sigma 1. So what? 350, right? And then 450, and so on. Right? So you're going to plot that. How are you going to plot? You know that is the sigma 3 and that's sigma 1. So you got what? A more circle, right? So here, right? When you take that is sigma 3, right? Here, right? You got the sigma 3 here, and that is the sigma 1 here, right? So you got sigma 3 and sigma 1. You can draw the more circle, right? Is that true? Yes or no? Yes or no? Yes. Okay, then say for the more circle, you have what? Here 150, right? And then sigma 1 is 350, right? So you got this more circle. Can you draw the more circle? Not by hand, by compass. You know what's a compass? And a graph paper. We are talking about accuracy, right? Do not sketch your graph. You have to plot your graph. So please bring along your, first of all, the compass. You know what's a compass? Yes or no? Compass. And then you have to measure the angle, right? So you have used the protractor, right? You know what's a protractor? What's a protractor? To measure what? The angle, right? The angle. Clear? So here, right? You got, say, 150, 350. So you got this small circle, right? Circle 1. And then you got the other circle here, right? Confine that's 200, right? And then say, right? And 450, and so on. So you can draw, right? Okay, so you got a series of more circles because got what? Sigma 1, sigma 3. You got 2 points, right? For the more circle. Here are the more circle, right? Sigma 3 and then sigma 1. And here, right? That is the sigma 3 and the sigma 1, right? Is that true? Okay, and then you got this, the third pair, right? right? Sigma 3 and then sigma 1. Okay, now try to draw the base straight line, which are touches, right? Touches the Mohr circle. That is called the envelope. Envelope. Right? That is the Mohr Coulomb. Sorry. The Mohr Coulomb envelope. Failure envelope, right? Failure. Because at any point here, that is the shear strength, right? The shear strength here. So the soil will fail by shearing, right? Shear strength of soil. So S, shear. Right? That's the normal stress. Here's the sigma, right? Normal stress. Okay. So what's the equation here? S is equal to C plus sigma tangent phi, right? What's the tangent phi? Here's the cohesion, right? C is the cohesion. And what's the phi? Here's the phi, right? You have to use the protractor, right, to measure the angle here. So by drawing the straight line touching all these 3 or 4 or more, right, more circles, then you have to lay down the base, right, more Coulomb failure envelope straight line. Then you can get the cohesion, right? C is the cohesion. Okay, that's your result. And here, the angle of internal friction. Okay. Yes or no? Okay or no? Okay or KO? Now, what about for after this soil lab test, right? You have a slope. You have a slope, right? Now, if you know the vertical stress here, right? Say 400, or what about 200? Right? 200 MPa, the sigma V equal to 200 MPa. And what about if the lateral earth pressure coefficient is 0.3? So what's the normal stress here? Could anyone tell me what is the horizontal stress here? If we know that the lateral earth pressure coefficient is 0.3 and the vertical stress 200 MPa, and what's the horizontal stress? Anyone? What's the horizontal stress? No one? What's the horizontal stress? Come on. If we know the lateral earth pressure coefficient 0.3, and also if we know the vertical stress 200, so what's the horizontal stress? By definition, right? K is equal to sigma V over sigma H. Sorry, sigma H over sigma V. Horizontal stress, right? Lateral earth pressure and the vertical pressure here, right? So if it is equal to 0.3, so sigma H and that's 200, right? So sigma h is equal to what? 0.3 times 200, right? Equals to what? 60, right? So that will give you a value of 60, right? So that is the sigma 60, right? And that is the sigma 1. Okay, sigma 1. So that is sigma 1. So can you draw? So that is 60, right? So that is 60, right? Sigma 60, and you got what? 200 here. So you draw a more circle. 200. Okay, 200 here. You got, sigma 3, 60, and that is 200. Now, if that semicircle lies above this envelope, failure envelope, what contour can you draw? Is the slope stable or not? Stable or unstable? Yes. If the slope having the more circle, right, lying below the straight line, then it's stable, right? If the semicircle or the more circle lies below this line, lies below the failure envelope, then that means it does not touch that failure line. Then the slope is stable. Okay, that's the conclusion you can draw. Okay, clear? And now we come again to stress and shock. Okay, now I think you remember or you recall there's a table, right? Different m values of n, and that is what we call the I3, right? The I table or table 7.8. Okay, so you have different values of I3, right? You have so many, right? What's m? M is the the b over z, right? And n is equal to L over z, right? What is b? So you got on plan view, you got the footing, right? So you got the b and the L, and then z is the depth, right? In other words, you got the loading area here, right? BL, right? And then you got what? See here, right? The Z, right? What's the stress here, right? What's the stress here? Okay, sigma Z, right? What's the stress due to the loading here, right? You got the the footing area, right? And you have a loading, right? Uniform distributed over this area. So you have to work out what's the M. Well, M is the B over Z, right? Say if B is 4 meters, and that's 3 meters, and if Z is 2 meters, so M equals to what? Right? B, right? Say 4 over 2 and 3 over 2. Okay? So you got what? Here, 2, this 1.5. So you look up here, right? M is equal to 2, and that is n 1.3. So you got this value, right? The I3 values. Of course, if you have different values, right? 1.6, so you have to do the interpolation, right? For the I3 values, right? If you have, different values of m and n. Okay, could you recall this topic? Yes or no? Yes or no? You work out the, the m, the values of m, n, and also the z, right? So you have applied, right? And once you got the Q, the I3, right? Once you got the I3, then you should multiply the, the load, right? That is the loading, right? On the footing, right? Okay, so that gives you the sigma Z. Okay, now we come to this part. Of course, this equation refers to that's the Q, and that is the the I3, right, for this, right, and you got the M and N, so that you can work out, say, for the point A. So the stresses at depth Z below A is given by what? The Q times I3, right? And what's I3? Well, depends on the BL, right? And you work out the, right, M equals to B over Z, and N equal to L over Z. Now, it's easy, right, for the calculation for the stress below the point A, because it's related directly to that table, right, for the showing the different values of the I3. But what about if we want to calculate here, for the point here? Now, I don't want to calculate the stress at the point A. I want to know what's the B. Well, it's very easy, right? So you should consider the area, say, by considering the loading, right, is fully covered the big rectangle. So if that is, the footing A, so that's A1 and that's A2, right? So A1 plus A2. So you got the I3, right? Say 0.05, okay? And then, because actually you do not have the whole loading area here, so you have to deduct, right, minus A2, right? So you have to remove the loading for the A2. So again, for the A1, A2, right, you should use this, right, as for the values of mm, right, the m and n, right, for the whole area. So you got this B and L, right? What about for the A2? A2 is this area, right? So you got, let's take some example, right? Okay. Now let me say use some examples. So that's, that is 4 meters, right? And that's 4 meters, right? And that's 2 meters, 2 meters. Now for M, and we want to know for the Z, right? Z is equal to, say, right, meters, right? So M is equal to what? For the A1 plus A2, So that is 6, right? 6 over 2, right? And n equals to what? That's 4 plus 2, right? For the whole area is 6. And this is equal to 4, right? 4 over 2. Of course, the 2, sorry, 4 over 3, right? We are talking about meters, right? The exact is 3 meters. Okay? Now, for the area A2, right? So what's the area A2? So area A2 is 2 over 3, right? And that's 2 over 3. So you have to work out the I, right? Say that's 2, 1.33. Say, for instance, is 0.04. And what about here? 2 over 3, 2 over 3. Say that is 0.06, like that, right? But you should minus, right? So you have to add up these two, right? To give you, right? What's the stress at the B? Okay? Okay? Why is minus? Because that is minus. Because that is minus. So you have to do the minus. You have to deduct the area A2 from the big rectangle. Okay? Now what about here? Now we have talking about that point. What about this point? If the point here, right? Say that is 4 meters. That is 4 meters. So say that's 2 meters, 2 meters. So what you should do is that you divide this into A1, A2, right? So here, right, A1, A2, and that's A3, A4, right? Now we are talking about this point. So area A1 plus A3. So if that is again 2 meters, that's 2 meters. That is 2 meters. That's 2 meters. 2 meters. So area A1 plus A3. So what's M? Is that equal to 3? Right? So what's M? M is equal to what? Now this A1 plus A3 is a big rectangle, right? So B is equal to 6 over, and N 6, that is 2, right? 2 over 3, right? You got the I3 here. And then you have to minus A3, right? Minus A3. Okay? So what's A3? 2, 2. So 2, 2. And the depth is 3, 3, right? And you got, say a certain value, right? And that's minus, okay? Because that is minus, so that's minus. Now, we have treated this part. What about for the other part? Exactly the same, A2 plus A3. So A4, right? That's A4. And minus A4, right? So again, similarly, plus minus, right? So you add up all this. So you can see here, right? A3 minus A3 plus A4 minus A4. So eventually you got A1 plus A2. Now that is what we are looking for, right? Because we want to know what's the stress at this point due to A1 and A2. So you add up all these things, right? Right? Say what's that value there, and then the sigma stress, the depth. Say if that's the the C point C, right? At the exact depth, 3 meters. That will give you what? right, times the, the footing pressure, right? That's the Q. Right? Okay. Yes or no? Okay. Let's take a break here, right? And then 10 minutes. 10. We will meet again 10 minutes later, and then we will do a harder one, right? Harder example. That is too easy for you. Okay. So take 10 minutes break. Okay, are you ready for the tutorial? Are you back? Okay, now let's take a look, right, for the calculation of the sigma Z at the depth of 3 meters below this point, M, due to two footings, right? For footing A, the foundation pressure is 200 kPa, and for footing B is 300 kPa, okay? Now, for the footing A, well, sorry, for the footing A, so we have considered, right, here, there's L, consider this, so A1, so A1, A2, A3, A4, right? So that's A1, A2, A3, A4, right? So what is the here? 2 meters, 2 meters, so that's 4 meters, right? And what about here? 5 meters, right? Is that correct? Because that is 3 meters and that's 2 meters. So 4 times 5. So M equals to what? 4 over what? 3, right? N equals to 5 over 3. So can you work out the I3? Okay? But you have to deduct, right? This one, right? For this one. A3, right? A3. What's A3? 3 meters. Okay? And that is what? 3 meters times 2 meters, right? That's 2 meters. Okay, 2 meters. So M is equal to what? M equals to 3 over 3, right? And N equals to what? 3 over 3, 2 over 3, right? So again, you got the I3, right? But here, Y3, you have to deduct it, right? So it's minus, that's plus. Okay? If that is X and Y, so X minus Y. So we have finished this part, right, for footing A. Is that correct? Yes or no? Consider the whole thing and you deduct that corner, right, A3. Okay? So you got here, right? You have to deduct this corner, right? The A3, right? Deduct the corners, right? The corner piece. Now, what about for footing B? For the footing B, now imagine, right? Here this, now 2, 2, 4, 2. So that gives you what? 10 meters, right? 10 meters times what? So we better draw that. Footing B, right? Now we come to the footing B. So, right? It is 2 meters times 2 meters. Right? So 2 meters, 2 meters. And what's that? 2, 4. So that is give you what? 8 meters, right? So that's 8 meters. That's M, right? That's M. And what about this? say 3 meters, right? 3 and 2 meters. So that is 3 meters. Okay, now that's the yellow part, right? We come to the yellow part. That's the yellow part. Of course, we have to divide it into. Now that's more difficult part here. Now if that's B1, that's B2, and B3, and B4. So for the big piece, right? For the big piece, well, that's 10 meters, right? And that's M. Okay, and that is, you know, B1 plus B2 plus B3 plus B4, right? Okay, now assume that's the total, the whole rectangle. So that's 5 meters. So you have worked out M, N, right? What's M? 5 over 3, 10 over 3, right? So you got the I3. Okay. Now you have to deduct this piece, right? This piece, B3 and B4. Okay. So B3 and B4. So B3, B4. Okay. So what's the B3 here? 8 meters. And what is there here? 5 meters. So you have to deduct B3, B4, right? So B3, B4, right? So 5 meters times what? 8 meters. So 5 over 3, 8 over 3, right? So you got minus, right? So that is plus something. That's minus, right? Minus B3, B4. And then what about this piece, right? B2, B3, right? And then again, so can I go up to here? Okay. B2, B4. So B2, B3, right? So it's this part, right? This part. So you cut it here. So that's part, right? So what is the M? So what's that's 3 meters, right? And that's 10 meters, right? So M is equal to what? 3 over 3, 10 over 3, right? And I3, again, minus, right? Something. Because you're deducting that, right? Because that is the whole area loaded. So you have to deduct that. Now, can you see here, right? If that is the green part, so that's the green part. So you are subtracting 2 times here. So you have to what? To add this piece, right? B2, so B3, right? Plus B3, right? So what's that part? Here, right? The B3. B3 is equal to what? 8 meters, right? And 3 meters, right? That is the B3, right? This part. This part. Because you have deduct times, right? So you have to add it 1 time here, right? So that is 3 over 3 and 8 over 3, right? So that is plus something. Now let's check. Is it correct or not? Now the answer is that the stress at M due to B1. Now let's take a look. Well, minus B2 plus B2 minus B3 plus B3, right? Plus B3 minus B3, right? And then B4 minus B4, So what about here? B1, B2, B4. So you are leaving with only B1, right? So that is the answer, right? So you simply, right, minus plus plus minus, right, and so on. So you got what? This, right? The I3 for this. So if that is, the say the Y, right? And you've got here for what? Okay, that is for no. Say, what should I do? That's A. So that's A, right? The value is A here. So A times 200, right? That is the, okay, we got all these things, right? Oh, sorry. That's due to the footing B, right? So you add all these influence factors, right? B and all these A. So 200 footing A, 200 times A plus 300 times B, right? Will give you the final one, right? The stress at the M. That's due to the footing A, right? I3 calculation, right? I3 calculation. That is for the footing B. Okay? Is that okay? Is that clear to you? Remember that for any footing, it's too easy, right, to work out any points within here, and also for the point here, right? But for this point, it's particularly difficult. Any point falling in this area, say here, right? Say here, any point here, right? You have what? Say A, B, C, D, right? So you have to work out the whole what? B, C, D, right? And then minus, right? Here, A, B, right? And then also you minus what? B, D, right? Sorry. You minus Okay. No, let me recap here, right? It's easy, right, to work out any point here, right, for the stress here, say, and at any point here, right? It's very easy. And also for any point within this area, it's very easy, right, to work out the stress. Say for this point, you just divide it into two parts, right? So the total area minus this area, total area here minus this, right? But for the point here, any points fall within at the corner here, then you have to work out what. So that is, right? Okay. So you have worked out what? That's A, B, C, D. Right? So we work out A, B, C, D, and then minus, right? Minus what? A, B, and then you minus C, D, right? But you have to add B, right? Because by doing so, A minus A, B minus B, right? And then C minus C, right? So A, B, C, D, A, B, C, D, minus AB. So here, wrong. Well, here, minus BD, right? And then you have plus what? B. So it's wrong here. Okay, so that's C. So A cancel A, B cancel B, and then what? D cancel D, right? And B cancel B. So you are leaving here the C, right? Okay. So for this piece, corner piece, you have to pay special attention. This one. Is that okay? So that's the trick, right? For any corner piece, you have to bear in mind that you will be double counted for any piece, right? For that corner piece, so you have to add once more. That will give you the right and correct answer. Okay? Now here, if there's a retaining wall, okay, and you have 2 layers of soil or 3 layers of soil. Well, that is, the C, phi, and gamma. C1, phi 1, gamma 1. The C2, phi 2, gamma 2, right? The C3, phi 3, gamma 3, right? Now, if there's a surcharge, well, depending on whether you are going to calculate the Ka or Kp, right? Right? For active pressure, what's Ka? Right? For the active pressure, so you have to use this formula, right? The horizontal pressure is equal to what? Ka sigma V, right? For active, active. What? Minus, right? Square root Ka, sorry, 2C, right? 2C. Right? 2C square root Ka, right? Remember minus 2C, right? What about for the passive? For the passive, right? If that is active, if that is passive, right? Equal to what? Kp sigma V plus 2C, right? Square root Kp. Now what's Ka? Ka is equal to 1 minus sine phi, 1 plus sine phi, right? And Kp, the other way around, right? Okay? And that's the surcharge. So we have reviewed this part, right? It was the active pressure and the passive pressure. Please take a look here. Okay. Now, suppose for this retaining wall. Now, tell me if there's, say, 3 meters, and the groundwater table is here, right? Say here. Groundwater table here. Okay. And that is, is 4 meters, and that is 5 meters, right? And if there's a surcharge, right? Here, C equal to, say, 2 kPa, 1, C1, gamma 1, say 16 km per cubic meter, right? Phi 1, 20 degrees, so phi 2, 30 degrees, and C2 equal to 0, and gamma 2, 17 K per cubic meter, and phi 3, say 35 degrees, and then C3 equals to 3 kPa, and gamma 3 equals to 18 km per cubic meter. Now, can you work out the vertical stress here? Here. Now, we want to calculate the stress, right? For any point, right, within this layer, because we want to work out the stress diagram. So tell me here for the point A here, what's the vertical stress here? Sigma A. Now vertical stress, right? Say vertical stress. What's the vertical stress here? Tell me what's the vertical stress at A. Now, if say there's 20 kPa, what's the vertical stress here? Well, The vertical stress is 20, right? Charge, right? Surcharge plus what? Plus what? Right? 16 times what? 3, right? Okay. 20 plus 16 times 3 meters, because it's 3 meters deep. Yes or no? Yes or no? Yes or no? Yes. Okay. What about for B? Sigma VB equals to what? Now, if that gives you 48, so that's 68. So you directly use 68, right, to add, right? Continue the adding. Plus what? Because here is 68, and then you have a further 4 meters, right? But please note, it's below groundwater. Right? So you have what? 17 minus 9.81 times 4. Is that correct? You have deduct, right, the pore water pressure from the unit weight of the soil. Yes or no? Okay. Now, once you got the, the sigma VA, then you have to work out the horizontal stress. Now, suppose that is the state, right? The active. Now, the active state. So, what's the horizontal stress? Okay, let me take here. What's the horizontal stress at A? Now, you got two paths, right? Now, for the point about that, and for the point below point A, is totally different. Why? Because you have different stress parameters, right? Yes or no? You have two different values for the cohesion and also the friction angle. So for the for the A minus, that is A minus, right? That's A plus, right? So what A minus? So once you got the sigma VA, you have what? Times the KA. What's the KA? What's the KA? Minus sine what? 20, right? And that is 1 plus sine 20, right? And then minus 2c, right? What is 2c? 2 times 2, right? Times square root of 1 minus sine 20, 1 plus sine 20. Is that correct? Yes or no? No. Okay. Now, what about for A plus? You replace this 20 by what? 30, right? Because at that layer, below that line, right, you are stepping into another, right, friction angle, right, 30. So replace that by 30. And what about C here? Replace by what? 0. Correct? Yes or no? In other words, you may have the point here, right, for the A, the stress, right, may have a different values, right, here. For anything about here is A minus, and that's A plus. Because you have two different pressures, right, for the point A at the boundary between the two layers. Similarly, for this part, also you may have a two different values, right, across the point B right here, layer 2 and the layer 3. Remember that. Okay? So you got this pressure diagram, right? Okay, then you can divide it into what? Say that's F1, that's F2, that's F4, sorry, F3, F4. You have a series of what? Rectangles and triangles, right? So you know that's 1/3 of the height, that's 1/3 of the height, right? So you can add up F1, F2 up to F5, F6, right? F6 is total active thrust, right? And then you work out what's the location for this, the total force, right? The thrust T, right? So what's the total thrust of T? Is equal to this F1 up to F6, right? The summation of F1, F2 up to F6. And what about the location of this resultant force? How are you work out the L? Well, very easy, right? Summation Fi Hi over total Fi, right? So you take the moment about the base, right? Take moment about the base. So you got F1 times H1, F3 times H2, F2 H2, and so on, right? You got the centroid or the rectangles and also the triangles, right? And then you work out the moment, right, equal to the force times the elevation, right, of the base or about the bottom of the wall. Okay, so you got this L. So that is the answer. That's the answer. Okay. Yes or no? Yes or no? Okay. Time's running out, so I want to complete everything, right? That I want to talk to you. Now, here, suppose you are going to find, right? So if that is a force to move, right, the wall into the soil, so and that's a surcharge. So you got what? The passive case here, right? Because you are moving the wall, right, into the soil, right? And for the passive case, what about for this case? If this force is going out, so that will give you what? That's a charge, right? So that is active case, right? So for this case, you have to use what? The sigma h, or the passive pressure is equal to what? Right? Sigma v, right? Here, right? Here. So if the h, right? Sigma v is equal to times what? Kp plus 2c square root kp, right? And for the active case, sigma v times ka minus 2c ka square root, right? Of course, kp is equal to 1 plus sine phi, 1 minus sine phi, right? And for here, right, ka is equal to 1 minus sine phi over 1 plus sine phi, right? Now, tell me what's the vertical pressure here? What's the vertical pressure? It's equal to what? Q plus what? Gamma h, right? If gamma is the unit weight of soil. So you got this point, sigma p, right? And that is the sigma what? A. Now remember this surcharge, right? If you have the surcharge, you have to add not only the gamma edge, but also the charge. Okay or not okay? So you develop this diagram, right? So that is the, the KPQ here, the KPQ, because you have the zero depth here. That's the KAQ, right, for this point. And you got the sigma P, and that's the sigma A. So you got F1 and F2, right? So what's the P required? F1 plus F2, right? And if that's the active case, so that's F1, right? F1. So that is P, that's F1, that's F2, right? So the total force is equal to what? P equals, so that is the passive, that's active, F1 plus F2. Okay? And of course, you can work out the L, right? Summation Fi, Hi over summation Fi. Okay? Let me turn to the active, the lateral air pressure. Now I will do a new sharing of the application first. Okay. Okay. Now, can you see the valve, right? For the example 8.1 for the chapter 8. Okay. Now, I want to teach you a very quick method, right, to calculate the here. Now you can see here. .1 so 8.2 now of course you can see the author right here. First of all, you have to work out all the forces, and then you can see here, you take the moment about the toe. A is about, okay, about the toe. the toe, right? Here the moment about the toe, right? The moment about toe. Now he also do a calculation for a moment about, right, the point middle point B, right? So that you come up with this moment. So in other words, the writer here do the moment calculation 2 times, right? First of all, to work out a factor of safety against overturning, so he must do the moment calculation about the point A. And then in order to calculate the bearing pressure, right, the soil bearing pressure, because here, right, he had to do, right, the moment calculation here, right? So that's why he has to do what? The second moment calculation. But in fact, you can do only once. It's already good enough. Now let me tell you about that. Now here's the base, right? Here's the base. You know, that's the B, that's the A, right? That's the toe. And that is the midway, right? Midpoint. Okay? Now, can you see that once you got this, you can obtain this value in a quick way, in a much quicker way. Now, I will tell you. Now, here, first of all, you have take the moment about A, so that is the MA, right? And then you come up with what? MB, right? So that's MB, okay? And then you have a vertical load, right? Vertical load is the what? The summation of this, right? Right? That is the summation VI, right? So that is the summation VI. Now, you don't need to work out this MB. Actually, you should say here, how can I get this? Well, you can see here, right? Now, if you want to get the MB, okay, so can you change this? Now, that's the point A, that's point B. Now, can you work out the MB from the moment about A? So, if you the moment about this here, so MA is equal to what? Well, MB is the moment, so remains unchanged, plus what? Summation of VI times what? B over 2. Because you have already worked out, right? You have worked out this. So that is the overturning moment about A, right? And you have worked out, okay, this, right? So you can work out MB. You understand? Do you see what I mean? Okay? So that is the, the example what? 8.2. Now, let us take a look. What's MA? What's MA? Right? MA is how, okay? What's MA? 180, right? So I better 180.044814, and then, right, minus what? Sorry, 180. Okay. Okay. So 180.4814 minus what? Okay. Okay. Minus what? Five oh four 504.33, right, equals MB minus 283.14, right, is the vertical weight, summation VI, times B over 2, okay? Okay, that's the moment about A. Okay, now what is the 503? You know, that is the, right, the, here, right, the restoring moment. So that is the overturning moment. The overturning moment about A, about the toe A, that is the positive, right? What's the negative? That's the restoring moment about toe A. Okay, so that is the summation of VI, right, times B over 2. Now, in effect, you come up with 503, right, here, right? It's the restoring moment, right, here, right? Okay, restoring moment about the toe, right? So MB is equal to what? If you work out, is equal to 100.86. So 100.86. So if you work out here, right, that's exactly equal 100.86. So you see what I mean? You don't need to do this calculation again, right? What I'm going to say is that, right, you don't need to do this calculation. You just use these figures, right? You can see here. You see what I mean? 180, right? 504, and then you got the M exactly, right? Right, 100.86. You see what I mean? You can work out the 100.86 directly, right, from the overturning moment calculation. So you save, right, a lot of time. Why bother, right, to do this calculation? Right? You know, you have to see here, right? Very stupid, right? You have to do the calculation here. Okay? Okay? Because you have worked out the overturning moment, right? Take the moment calculation about the toe A, and also the restoring force about the toe, right? Then why do we need to do the calculation by taking the moment about the point B, right? Again, just, for a separate point. But use this formula, right? Here, right? That's this formula. Because you have come up with the MA, right? Overturning minus, the restoring moment, overturning minus restoring moment, and you know the total vertical weight, and then you work out the MB, right? And the MB into your, the soil bearing pressure calculation, okay? Now, of course, if you are not familiar with this, this formula here, right? You just ignore my, my teaching here, right? And and follow the calculation as shown in the teaching notes. What I'm going to say that there's a shortcut, right? Not to take the moment calculation again, although at a separate point and at different points. Okay. Now you can check with your assignment, right? It's true, right? That equation can be verified, right? With your, your previous assignment calculation. You can try it if you have time, right? If you don't understand, well, you just ignore my teaching here, right? And do your own way of calculation. Okay? Is that clear? Okay, I will stop here, right? So, anything you want to discuss? Now, if you try the past exam calculation, right, and you have done that, then you better, put it in a PDF file and send email to me, and I will give you the numerical answer, right, not the solution to you. Okay. So, any question? If no further question, I'm going to leave you now. Okay. Bye bye.